지훈이 시작하실까요?
네, 시작하도록 하겠습니다. But before we start, make sure that you have the access to the GPUs and you already have installed PyTorch. And if you are using Colab, please so click Runtime. And if you click this one, then there is you can choose anything. So you can in here you should use GPU to for this lecture. So we'll start. So in week 3, we'll use PyTorch, and by using PyTorch, you'll learn about logistic regression and multilayer perceptrons. So in this lecture, we'll cover the basic concepts of PyTorch framework, the tensor operations and GPU utilizations, and mainly the Autograd, the automatic gradient calculation. And we'll implement simple logistic regression and especially multinomial logistic regression, and use multilayer perceptron in this class. So if you have any question, feel free to ask. And for additional question, you can send emails to me or post question in the class. Okay, so why PyTorch? There is lots of deep learning frameworks in modern era, and mainly we use two, the PyTorch and TensorFlow. So PyTorch is more intuitive, and defined by run method. TensorFlow is defined in run method, and this is a little bit confusing to the beginners. And it is really compatible with NumPy. I think we already learned about NumPy in last week. So as you can see, in the modern real deep learning conferences, more and more PyTorch users are coming. So before we start, we have to load packages and we have to set up the GPUs. So if you run this code, you will see the GPU utilization. For me example, you can see like this. And then you should set the GPU number. So this means that I will going to use GPU number 0. And please load the package and check your PyTorch version. So for me, it is 1.5, and if you're using Colab, it will be 1.6. So PyTorch and NumPy is really similar. So it is almost so it's almost one-to-one mapping. PyTorch uses tensor. This one is tensor, and it is the basic data structure in PyTorch. So it's an n-dimensional array, and you can use GPU calculation with this tensor. So since I said it is almost one-to-one mapping, we'll see what is similar and what is different with NumPy. So we will not cover everything, but if you go inside this GitHub, there is comparison with NumPy and PyTorch, and we'll cover a little bit in here. So there are same operations with identical grammar, and this is easy to use. There is same operation with different grammar, and there is some different operations with same grammar, and this is really confusing. So first, we define NumPy array like this, right? np.array, and in PyTorch we use torch tensor. So it's the same thing. So if you run this code, we will have NumPy array like this and torch tensor like this. This is the basic building block of PyTorch. So first we will see the same operation with identical grammar. So it's the same with NumPy. So when you use tensor, you want to know the shape or the size of it. So in NumPy we use shape, and identically in Torch we use shape also. And there is a size operation which is the same with which is the same as shape operation. So as you can see, if you run this code, we can get the shape of the tensor. So as we defined like this, the shape is 4, and we only have dimensional 0 in here. And second thing is there is the same operation with different grammar. So there is so if you want to concatenate two tensors, NumPy use NP concatenate. However, in Torch we use Torch cat, and it does the same thing. And the most important thing is that NumPy use axis, but in Torch we use dimension. So it's two things are identical. So we want to concatenate these two things. So MPRA1 and 2. In Torch, we use the same with cat, and you should change to dimension. So this is exactly identical thing. So, and sometimes you want to reshape the tensors, right? So in NumPy, we use reshape, and Torch, we use view. And I saw that Torch also have reshape version, but I would so if you we have a tensor with shape 8 in dimension 0, and we want to reshape like this. In dimension 4, we want to have 4. In dimension 0, we want to have 4, and in dimension 1, we want 2. Then we can reshape like this, and the shape will change like this. And this one is a little bit confusing since the operation is different, but they share the same grammar. So there is a repeat operation, repeat grammar. So as you can see, we want to repeat this one. And if you write X repeat in NumPy, and if we run the same operation in Torch, it will have a different output. So NumPy, it repeat 1 twice, and then 2 twice, and 3 twice. However, in Pytorch, we repeat like this. So we have 1, 2, 3, and then repeat 1, 2, 3 again. So if you want to obtain the same result like NumPy, then you have to do some reshaping and repeat on the different axis, and then reshape it again. So it's more complicated, and so it can be confusing to Torch users. And also, this manipulation task can be used with stack. So we use the repeat in Torch, and there is a stack operation in Torch. And if you run stack, then we stack like this. So if you want to have a same result with repeat, then you can repeat and reshape the tensors. There is many grammars in PyTorch, and if you go inside Torch official homepage, there is a docs. So if you have any questions about it, then you can actually find every operations here. So there is a description of it. And if you want to see the compatibility with NumPys, then you can see this GitHub. So this is the review of PyTorch, and we will do GPU utilization using PyTorch. So GPU, we use GPU for fast calculation in deep learning frameworks, and in this section, we will learn how to utilize GPU in PyTorch. So first line is Torch CUDA is available, which means is GPU accessible. So if you set the GPU in the first place, we already have that line, then it will print true. So I defined some torch tensors. So torch 1 means that so torch 1 means that it's repeating 1 like this, and rand n means generating random number with this size. So we have generated. If print the device of it, then it is inside CPU, but we want to use it on GPU, right? So if you add this one, and since A and B is on CPU, C is on CPU also. But for fast calculation, we want to upload A and B to GPUs, right? So we already have access to the GPU. So A to CUDA means it's uploading to the GPUs. After this line, we have A device as CUDA. And it says 0. Since we set the GPUs to 0 in the first place, it's CUDA 0. So if you have other types of number, so if you have like 4 GPUs and you set the GPU number to 3, then it will have CUDA 3. So we'll add A and B. And since A and B is on the GPU, C is also on GPUs. However, we have a storage limitation, memory limitation in GPUs. So sometimes you want to use your tensors in the CPU. Then you can just use this line. So C to CPU, then C is removed from the GPU. So you can check device. So whether the tensor is on GPU or CPU, and you should use 2 operations to upload or detach from the GPUs. This is how you utilize GPUs in PyTorch. Next is Autograd. So Autograd is the main concept of PyTorch. It automatically get the differentiations of tensors. And if you want to use, so this is some examples using Autograd. So first, since X wants the gradient, we have to set requires grad true. And we'll see, we'll plot X, then as you can see, we have requires grad true. And then we'll add 2 in here. Then the Y will have this shape, right? And then we can also define G like this. And now like this. It's just getting the mean of this matrix. And then what we have to do is retrain grad is retraining the gradient computation. And if we use backward, then it will calculate the gradients. So as you can see, out is the mean of the G. And if we want to calculate the gradient, then it will be 1/4, right? So if we print the gradient like this, we have the same values. Next, if we want to calculate the gradient of Y, we have the same, we can just compute the chain rule like this. So it prints tensor with this shape. And then we can also compute the gradient x, and which will be the same due to the chain rule. But if you run this code, it will have some it will take some computations since we did the require grad in the first place. So Torch computes all this y, x, y, and z in a computational graph and save it, since we want the gradient after the backward. However, sometimes you don't want to calculate the gradients, right? So if you are just testing or using inference, then you want to do memory efficient way, and you don't want to compute all the calculation graph in your memory, right? Then you can use Torch no grad. Then it is more faster, but it doesn't generate any computational graph for backpropagation. So if this is the same code as above. And if you run out, then we have the same value. Then after we use out and we do the backward, it will have some error like this, since we used Torch no grad, so there is no computational graphs in the PyTorch. I have some questions. So what does requires grads does? So so as you can see, we want to compute the computational graph. I will answer one by one. So first question was, what does require grad does? So in the require grad, so you're going to use this tensor in the computational graph, and then the backward is backpropagation, which means you're going to calculate the gradients. So if you don't write this one, then we cannot calculate the gradient, because we are not going to use, we are not going to omnode to this tensor in the computational graph. So the next question is that, yes, so graph. Yes, so if you run backward, every the gradient flows in the computational graph, and you should use retrain grad to retain it. So if I'm not using retrain grad, then the gradient flows, but I'm not going. It will not save the gradients in the y. So I will run this code again. Because we didn't use retain grad, we are not going to save the gradients in the z. However, if we train the grad, when we flow the gradients, it saves the gradient information in z, and then you can. Sorry, I have to do it again. Then we save the gradients in the z variable. So I think this is. So what if we not use no grad and x gradient for false? So later on we will use model. It's called mn.module, and if you forward that in the mn.module, then it automatically generates computational graph. So for example, you will learn about CNN, ResNet, or something like that, and it's a really big model. And if you don't use torch.no graph, then it will compute all the computational graph in your memory, and it is non-efficient for testing. So you can also use require grad false in this case. However, in the later on, you should use torch no grad for the fast computation. So Y, Z, and Y and Z are retain grad and out is backward. So backward mean I'm going to flow the gradient from the out. So you can do D point C dot backward, but then we will calculate the gradient from C. As you can see, the computational graph will be like flows like this. So if you do Z backward in here, you can also get the Z and X grad. However, we cannot calculate this. So we don't have any computational gradients in here. So back propagation. No, so the graph. So we computated X to Z, X to Y, Y to Z, and Z to out, right? Then the back propagation goes backward like this due to the chain rule. So if you run backward like this, then the gradient flow like this. This is forward, right? So I think
여보세요?
there any...
지훈님.
네네.
제가 잠깐만 그냥 한마디 더 하자면은, so when you call backward, what you're essentially doing is 여기. So when you call backward out dot backward. All right, this is really bad writing. When you call out backward, what this equals is you're doing D out by dx. So this is what backward does. And if you want to do d out dx, this actually needs to be broken down into chain of derivatives. D out, dz, dz, dy, dy, dx. So if you don't do retain grad like this, if you don't declare retain grad, then these values will be thrown away. But if you want to save these values along the way, then you have to call this retain grad. Otherwise, you're going to be left with only this value. If you want to save this all the way, then you want to have the retain grad all the way. So backward is basically doing derivative. Retain grad is storing the chain of derivative values along the chain. So that's the difference between the two. Let me see if there are other questions that I should answer. 백프랍 순서가 YT. 백프랍 순서는 꼭 그렇게 될 필요 없어요. 근데 그러니까 Y랑 Z는 retain grid. So the order between Y and Z retain grid doesn't really matter as long as you call them before you call backward. It's important to call retain grid before you call backward because, as I said, retain grid is actually doing the derivative. It's like a Q sign. So before you hit the Q, you want to clarify that you want to save the gradient values. So you have to. It could be Z retain grid, then Y retain grid, but as long as you put them before out backward, you're fine. 네, 된 것 같습니다. 네, 계속 진행하시죠.
네, 감사합니다. So we'll move on. So we'll learn about NN.module. So if you're using PyTorch, there is, they already implemented lots of things inside PyTorch, and NN.module is about the models. So if you can customize any models that you want in PyTorch using this library. So first, you're going to import this library. And this is just for, we'll define a tensor like X in here. And the shape will be like this. And what we're going to do is we are going to learn a linear model. So just simple regression model. Then we can define the linear FN like this. Then as you can see, what we're doing is the input dimension is 3 and output dimension is 1. So if we calculate this one, then it's just calculating WX plus bias term. So in picture is 3 and out picture is 1. So if you run this code, you can see that the this 3-dimension go to 1-dimensional tensor. Since we have two tensors, the torch size is like this. And if you summation all the elements, then we can have the tensor like this. So there is lots of types of NM module inside PyTorch. So there is convolutional network, RNN, LSTM, and even transformers are implemented inside PyTorch. So you can just use PyTorch NN.convolutional and use and you can design your customized model. Yes, so in the first place, so someone asked that is W and B is random? Yes, it is random, and there is lots of randomization method. For example, there is Javier initialization or Kyming-Hess initialization. So this is in the first time it is set as random. So when you're designing customize your network, you can use NN.module like this. And then if you inside NN.module, you have to define forward. Then what it does is after you define your model like this, actually you have to input dimension to, for example, 32, output to 1, hidden to 1. And what can we do with this is we can just operate a tensor which shape has to be input dimension with 32. Then if we use like this, then A goes inside to the model and just calculate all the things and return X. Then, for example, A will go in here and it will meet linear 1 layer and then ReLU activation and then linear layer 2. So this is how you customize your model, and you can design any model with this NN.module. And as I mentioned, there is a ReLU, which is an activation function. And the activation function is really important inside deep learning. So it makes the non-linearity of deep neural networks. And therefore, we can use it for approximating complex functions. And there is lots of activation functions inside PyTorch, and it is already implemented. So sigmoid or ReLU is really oftenly used, and you can use with NN modules. So this was the basic things in PyTorch. And from now on, we'll do MNIST classification using PyTorch. So it's a multinomial logistic regression task, and we will extend it to multilayer perceptrons. So first thing is, what is MNIST and how to do multi-class classification. So this is the MNIST dataset, which is a handwrite digits from 0 to 9, and it has training set of this size and test set of this size. So what we want to do is, if we have this single image, we want to classify which number it is. So for example, this is 3, this is 4, and this is 2. So this is a multi-class classification problem. So we have to handle with this multinomial logistic regression. To do this, we use softmax probability. So as you can see, this is a softmax. Since the ESI is normalized with all the classes, it's a probability score. And how to train this is we cross-entropy loss. So what this is so you will have a softmax probability. For example, this 7 comes in, then we will have a probability of 7, like 80%. And what we want to do is make it to 100%. That is what cross-entropy loss does. So this is the basic concept.
좀 해주실래요?
네.
질문인데 답을 좀 해주실래요?
질문이 W와 B 랜덤으로 설정되는 건가요에 대한 질문 말씀이신가요?
예, 맞습니다.
네. So it is random, and there is a randomized method. There is also a randomized method like Javier initialization or Cunningham initialization, and you can choose anything. So this is the W and B's are inside the linear, and it is also it is randomly initialized. So we'll do the MNIST classification. So first thing, you have to load the packages, and then we'll load the data sets. So if you run this code, it will, if you don't have the MNIST data set in this route, it will automatically download from the homepage. So MNIST data set is already implemented inside Torch Vision, which is a Torch library for vision. And then we can download the MNIST data set to train data set and test data set into test. What transform does is that, so the MNIST data set, every data set will be transformed with this transformation operations. So first thing, you will have a like PNG file or JPG file, right, for images. Then we want to transform into tensors, right? That is what this transformation does. And then we should define a data loader, which is the loader for training data loading library, data loader. So which what it does that if you run the iterations, it will automatically shuffle the batches inside all the training data set and then load the batch one by one. So next, we should define the model to train the MNIST classification. First, we'll do multinomial logistic regression. I think the question is already answered by Professor. So the question is the self-linear one, self-linear one. So this is just the customized name value. So you can use anything. So you can use any values like this. Why do we shuffle the training set and not the training? The conclusion is that we need randomness for the training because we use stochastic gradient descent, which is the and the randomness is really important in this optimization technique. That's why we shuffle the training set, but we don't have to shuffle the test set because test set is just for testing. So we shuffle all the training set and then get the batch. For example, if your training set is like 1, 2, 3, and 4, and the batch size is 2, then if we shuffle the whole training data set, it will come like this, right? In the first place, if you get batch size of 2, then first batch will be 1 and 2, and second batch will be 3 and 4. And if you shuffle it, then the first batch will be 4 and 1, and second batch will be 3 and 2. In every epoch, we'll explain about epoch in the later section. In every epoch, the train loader shuffles the whole training data set. So yes, so we have the percentage. Yes, so we'll define our model. So this is multinomial logistic regression, right? So we have input size, and then output size will be 10, since we are going to do 10-way classification. So we already defined multinomial logistic regression. The input size will be 784, since the MNIST size is 1 channel and 28 pixel and 28 pixel. So 28 by 28 is 784. So we have an input size of 784, and the output class will be 10. So we use 10. So we'll define a model. And if you print this model, we have a 1 linear layer, right? And then what we want to do is upload the model to GPU. So you can just run simply model to CUDA. To learn the deep learning model, it's all about optimization. So, and we should define an optimizer for such model. And there is lots of optimization techniques in deep learning. We will not mainly cover all this stuff, and you can take this course for more information. So if you see this GIF file, so our optimization goal is to get to the lowest point, right? So SGD, which is the red line, goes like this. And if you use other optimizers, you can go more faster, right? And in this class, we'll use SGD with momentum. So momentum is this green line, right? And mostly people use SGD with momentum or Adam optimizer. This is a really stable optimizer. So for defining optimization, so what we want to optimize is model's parameter, right? So we want to update the model's parameter to learn a model. So the input of the optimizer is model parameter, and this is the learning rate, which means when we have the gradient computation, how much how far do we want to go? This is the concept of learning rate. So you can increase learning rate to 1.0, but it will not work well. So you have to, this is a hyperparameter, and you have to carefully choose these parameters. So we'll choose SGD with momentum, and then we are going to train the model. So as I mentioned, we are going to use cross-entropy loss, and then we will run this code. But I have an error in this section, so you should remove image shape. It prints all the batch size, so you should remove this one. How can we choose the value of error? So as I mentioned, it's a hyperparameter, so you should try lots of values. So mostly we use this value in images, but in other domains we use other values. If you're having problems with choosing learning rates, maybe a good option will be just using Adam with this learning rate, because it has a learning rate adaptation algorithm inside Adam, so it's much more stable. So what it is, so if you for loop the train loader, then you will get a batch of images and labels. So we set the batch size of 128. So we'll have the shape of that, and we'll get the images and the labels. What we have to do is upload to GPUs for the fast computation. And then just forward the images to the model, then you will have the outputs, and then calculate the loss, the cross-entropy loss. And with the optimizer, you just optimize the loss, then it will automatically compute and update the model parameter. So it will take some time. So as you can see, there is the optimization is going on. So what Epoch is doing is you have total training set, and then how much time you're going to train whole training set to the model. So as you can see, the loss is going down, which is a really good situation. And after running all this code, we are going to validate with the test set.
지훈님, 제가 잠깐 뭐 하나만 설명할게요.
네네.
제가 화면을 제 거를 공유할게요. 잠깐만요.
네. So what does Autograd does is that it zeroes out the gradients. So after this zero loss backward and optimization step, we have to zero out all the gradients that we have computed in the before step.
지훈님 화면 공유를 좀 꺼주실래요? 제가 공유를 하려고 그러니까 안 된다고.
네, 알겠습니다. 잠시만요. 공유 중지된 것 같은데 혹시 되었나요?
제가 이제 할게요.
네.
보이시죠, 제 화면?
네네, 잘 보이고 있습니다.
Okay, so I just want to say, okay, so I think we should just check on one thing, which is that if you remember the logistic regression, there was the sigmoid function that that forces your output to reside between 0 and 1, which basically makes your classifier a binary classifier. But here, we're not actually doing binary classification. We're doing 10-way multi-class classification because there are 10 digits, because MNIST consists of digits 0 to 9. So it's a 10-way classifier. So it's no longer logistic regression. It's a multinomial. It's a multinomial logistic regression, as specified here. So what actually happens is, let me draw a simple picture. You give a image, which is just pixels, and then this goes through a, let me see. All right, so let's say this is 28 by 28, and 28 by 28, then this should be 10. What this is a weight matrix. This is 10, this is 28 by 28. It's a weight matrix. This is your input X. And what happens if you do a dot product or matrix multiplication between the two, between X and W? So that becomes a 10-dimensional vector. So this becomes a 10-dimensional vector. And of course, this will be just 1. So it's a column vector of size 10, and each coordinate or each dimension in your 10-dimensional vector, like first dimension, the second dimension here, the third dimension here, the fourth dimension here, they denote the probability, or it should be like the potential, not the probability, because the values here, they reside between negative infinity and plus infinity. So the values here would be negative infinity to positive infinity, because it's just a simple Wx. This is your vector y. This is your vector x, and this is your y. And currently the value of the y is negative infinity to positive infinity, and you want to force that to become a proper probability, which is that currently here the first value, whatever the value is, it just represents how likely it is that your x is the digit 0, because n is starting from 0 to 9. Each coordinate represents how it is likely, or the power of each coordinate. No, not the power. It's the potential of your x being a certain digit. So it is not a probability yet. So you want to make that into a probability. You want each value to reside between 0 and 1, and you want the entire thing, the entire sum, to be to 1. Because it's a multinomial distribution. So it's a categorical value. So the entire the value, if this y should be a probability, then its sum should be 1, and each value should reside between 0 and 1. So the way to force this, the way to make it into a probability is to put it through a softmax. All right, this softmax. Right. So softmax function is what makes a multinomial potential or power converted into a proper probability. So, and the mathematical expression of softmax is, we can just look it up actually. This is a mathematical expression here. Right here. So it kind of looks like a sigmoid function, but it's just that there's exponentiated. So beta zi is this value here. This is your potential, basically. potential or likelihood or unnormalized probability of your input being a certain class. So you want to you put a you exponentiate it with the Euler constant, and then you need to normalize it because this alone is not a probability. You want to make it into a probability, so you need to normalize it with a denominator that looks like this. So that is supposed to happen, but it didn't happen in our code here. There is no softmax function here. So originally, if you put so there should be one more line here that says self. Torch, and then something like softmax here, and then this. So you need to encapsulate your output, which is this one. This is your output. You need to encapsulate or put it through a softmax function. Looks like that. Looks like this. I'm not really sure the syntax is right, but it should be something like this. So you should have a softmax function in front of your output, so that your out is actually a probability. So if this is out, then props are torch, and then that's softmax. But we are missing. So if you do this, if you have the softmax function and then you take the props out, then this becomes a proper multinomial logistic regression, which is basically a maximum entropy classifier. So you need to do this to make it into proper probability classifier, but we didn't, because the reason that we didn't do this is because if you go down, we are using something called cross-entropy loss. So cross-entropy loss, if you look it up, let me just erase all of this. Oh, sorry. All right, it's already there. Okay, so if you look up cross-entropy loss, it says that this criterion combines log softmax with negative log likelihood loss in one single class. So it already, this loss here, this cross-entropy loss already includes the softmax function inside and then puts the negative log likelihood on top of it. That is why you don't need to put a probability explicitly in your multinomial logistic regression, because when you're using cross-entropy loss, it is already assuming that you didn't put softmax here, so it is doing its job for you. Cross-entropy loss already has softmax inside, so that is why you don't need to put softmax here in your original classifier. So I just wanted to make sure that everybody understands what's going on here, because I think somebody would probably ask why we didn't use softmax or sigmoid in this function. That's because we're using cross-entropy loss. But when you don't use cross-entropy loss, and when you just define your own loss, if you just implement cross-entropy on yourself, then you need to make sure that you put softmax somewhere, at least in the classifier, or at least in the loss function, somewhere that you need to normalize it into the proper probability values. Let's see if there's a. 그렇죠. 김재균님이 지금 하셨는데, 그러니까 모델 마지막에 소프트맥스와 같은 액티베이션 없이 정의한 게 맞나요? 아니에요. 그 맞지 않습니다. 그냥 단지 우리가 크로스 엔트로피 로스를 썼기 때문에 이 소프트맥스를 안 써도 되는 거예요. 만약에 크로스 엔트로피 로스를 안 쓰면은 소프트맥스 쓰셔야 됩니다. So if you use zero grad on each epoch, not on each mini batch, that's just weird, because you update your parameters per mini batch. So that is why you need to reinitialize your grads into zero values, because you do mini batch update. I mean, you update your parameters on each mini batch. But if you want to use zero grad on each epoch, then that means that you want to update your parameters on each epoch, which is just very inefficient. Batch size 어떻게 정하는? Batch size. So how do we define batch size? That's just based on your experience. So if you have a huge model, then you want to use a larger batch size, as long as your video memory allows. So, and if your models are really small and your entire data set is small, there's no reason to use a really large batch size. But yeah, there's a subtle relationship between the batch size and the learning rate, and there's a really long, like gigantic, like dozens of pages of report or academic paper on that. Like what's the optimal batch size and learning rate all together. So if you're interested in that, you can reach out to me and then we can discuss. But basically, it's all based on your task and your model and your data set size, the optimal batch size. All right, and if you don't use your grad, you'll accumulate all the gradients from the previous set. That is correct. Yeah. So yeah, Wilmer hit it right. Joshua Julio. How do we optimize the number of epochs? The number of epochs, the longer the better. So as we didn't use a validation set here, but if you use validation set, then each after each epoch, you want to evaluate your model performance against the validation set. And as soon as it starts to degrade, that's when you want to stop. WX를 계산한 Y 하나의 디멘션 값은 WX를 내죠. 가깝신가요? 그래서 계산한 Y 해수의 하나의 디멘션 값은 WX 해수를 내죠. So the question is, 아니 저거는 내적이라기에는 요게 X고 요게 W. 사실 그림 하시려야 돼요. 여기 이거 하나는 얘 전체에다가 요거를 내적한 값입니다. So the first dimension of your output Y, which is the probability of your X being digit 0, is basically your X inner product with the first column of your weight matrix, the first column, which represents digit 0, and the last column represents digit 9. So that's what this value is. If you do an inner product with this, then you get the last value. 라벨도 어떻게 W 간 거야? 없나? 어떻게 W 간 거야? 라벨이 없냐? 무슨 의미시죠? 이건 백프랍으로 학습을 하지 않아요, W를. 그래서 라벨은 있어야 됩니다. 요 X가 0인지 9인지는 다 라벨이 있어야 돼요. 이폭 글씨 0까지 각각 의미하게 되는 건가요? 아니요, 전혀 그렇지 않습니다. 지금 이폭 하나의 이폭 안에 so a single epoch consists of your entire data set, which is 10,000 images of 0 to 9. So one epoch is like hitting a single epoch is equivalent to that your training process has gone through the entire data set once. So if you're on 2 epochs, that means your entire training process, your mini batch update, has gone through the entire data set twice. Okay, so that's what epochs are. So your epoch your single epoch consists of all the digits from 0 to 9. And actually your mini batch will consist of digits from 0 to 9 because you want to shuffle them as randomly as possible. When you do stochastic gradient descent, you define a mini batch, and you need to define a mini batch in a way that it is as much as randomized as possible. Otherwise, it doesn't work. If your mini batch consists of if your mini batch is like a sequence, or if your mini batch consists of only zeros or only ones or only nines, it doesn't work because there's dependency between your samples. 소프트맥스에서 가장 큰 프랍이 나온 값을 리에서 네 맞습니다. 하지만 so that 주윤상 asked that before softmax, even before softmax, and even before the proper probability value, your linear outcome is still representative of the true class, because the largest value here, if some coordinate has a largest value, then that means that value, that coordinate is the true class, or the predicted class, to be more precise. It's just that you need to normalize them into probability value in order to use negative log likelihood loss. Because negative log likelihood loss and the cross entropy, all that depends on your output, y, being a probability value. You could try that, but I'm not sure if that would work as effectively as doing softmax and NLL. You could try that. Yeah, I don't have the time to actually derive what would happen, so I'm just going to jump through that. Yeah, if you try that and then if you find something interesting, you could share the result on class. Whatever the training again, first I did your best time. First I did your part, share parsa가 나오는데. I think that's
주석 처리해 주시는 거예요.
128 by 784. 784 is 28 squared, so it's a single example, and 128 is your batch size. Okay. Print. 네 맞습니다. 감사합니다. Okay. So I think I've answered all the questions. 지훈님 다시 시작하실래요? 그러면은?
네, 감사합니다.
네. 저는 공유를 그만두겠습니다. 네.
So we'll restart. So I think everyone has finished the training process. So we are going to test the model. So we in the test model, we are going to use Torch Autograd since in the first class, in the first section, we already talked about this. So for the memory efficient way, we will use Torch Autograd. And then in here, don't forget to use test loader and then do the same thing. So this is getting the maximum prediction. So Torch Max will give the maximum prediction label, and then we'll check the correction. And then we can divide the corrected sample with the total set. Then we can get the test accuracy. So as you can see, we have a we have an accuracy of 92, and then we will move on to multi-layer perceptrons. So in here, as you can see, we are going to define some multi-layer perceptrons with some hidden units, hidden layers, and sigmoid activation. You can customize anything. So you can use ReLU or other things, or you can increase the layer size. So this is your network, and everything is same except for this model. We have used multinomial regression in the first place. However, you're going to change just this line into your networks, what we have defined in here. And every code is same, and we will run this code. Until here, do you have any questions? It will take some time to train this model. Yes, you have to choose by your experience. So you have to try everything. So FC is like fully connected. It means fully connected layer, which is just linear layer. So I think that. Also, model eval. So when we will not cover in this class, but if you use dropout or batch normalization, such things like that, then there will be a training mode and an evaluation mode. For example, in the training mode for batch normalization, we update the mean and variance. However, in evaluation, we should not we should not change the, we should not update the mean and variance of batch normalization. So we do model eval, but model eval and torch no grad is different. Model eval is just what I said is we just do not update batch normalization, or we turn off the dropout. That is all we do with the model eval. And the image, so this is the size of batch size. So we have a mini batch of size 128, the size of the mini batch, and we have 469 mini batches on total training data set. I think we should check this question. I don't know what other libraries have implemented it, but in PyTorch, we don't use softmax layer for cross-entropy loss. Yes. So the final dimension will be 128, the batch size, and the dimension of 10, since we have the logic, we have the number from 0 to 9. So we have the training in there. Build this model. So as you can see, the accuracy have increased. The prediction, yes, the predicted size will be, I have to print it, maybe different. So it's size of 100. So in the Torch Max, it doesn't calculate the final dimension. So if you want to have a better model, you can change the size of hidden layer units and number of layers or types of activation functions. So predicted, the reason of predicted. So we are getting the max logic, which means the maximum probability, right? So maximum probability means the most likely predicted label. So we use predicted variable name here. And also you can choose other learning rates, epochs, or other optimizations, or momentum hyperparameters as well. So you can try it by yourself, and then you can obtain more better accuracy. Thank you. I think I covered all the materials today, and if you have any question, you can feel free to ask. Oh, so first question is that why do we do bar and predict? So Torch Max, if you look at the documents of Torch Max, it returns the maximum value and also the predicted index. So for example, Torch tensor, and you have 1 and 2 and 3. We'll just erase this one. The prediction, the maximum value of A is 3. However, so I think I have some help. So we want to, so what we have done was we want to know the index of the returned value. So the maximum is 4, but the index of 4 is 0, 1, and 2. So what is momentum hyperparameter? So we used SGD with momentum, and you can change other momentum parameters. So in here, we have choose momentum is 0.9, and you can choose other values. Can we see the weight value after the optimization? Yes, you can see the weight values after the optimization, and you can print. I don't know how to print the model parameters, but maybe this one. You have to check it, but I don't know the exact grammar for this. But you can print it. Yes, so you're getting vectors of size 100, and this. So the batch size is 100, and you will get the predicted indices of each elements in the batch in the test batch. So so the loss backward and optimization step. What we want to do is optimize this loss, right? So if we do the loss backward, we'll calculate all the gradients, and then we do the optimization step. Then the optimizer will update the model parameter. So this is just so optimizer. We have we have a computation graph for model parameter, and then we do loss backward. Then, as you already see in the first page, in the first sections, the model calculates the loss backward calculates all the gradients, and then optimizer use that gradients to update the model parameter. How to check mini batch size? So in the data loader section, we already we have defined the batch size with this size, but you can customize. You can reduce batch size or increase batch size. So the next question is, CPU memory to GPU memory is slow. However, when we use train loader, first, every images and labels are already inside CPU. So we have to, in every iteration, we have to update to upload to GPU. You can upload every images into GPU if you have enough memory, but you will, most of the case, we don't have enough memory. Instead of output data set, data. So, what was the first question? 이원준님 혹시 질문 어떤 거 하셨는지 다시 한번 말씀해 주실 수 있나요? 이제 빠르게 한국말로 설명을 드리자면 토치 맥스라고 했을 때 제가 지금 찾아봐야 되는데 이제 인풋이 들어왔을 때 이제 맥스 값만 원할 때도 있는데 동시에 인덱스 값을 원할 때가 있어요. 예를 들면 뭐 0, 뭐 이런 예시에서 이제 맥시멈 값은 이제 두 번째잖아요. 근데 두 번째 에라는 이제 정보가 필요할 때가 있는데 그럴 때는 이제 맥스 a,1을 해주면 이제 리턴 값이 두 개가 나오거든요. 그래서 첫 번째 리턴 값은 최대 값이 나오고 두 번째는 어떤 것이 맥스 값이다라는 정보가 나와요. 그래서 그 두 번째 값을 얻기 위해서 이제 맥스, 1을 한 거고요. 그리고 이제 언더바라는 건 뭐냐면 리턴 받은 밸류를 뭐 딱히 저장하지 않겠다라는 뜻입니다. 그 두 번째 박성진님 먼저 제가 답변을 빨리 드리자면 output.data는 뭐냐면 아웃풋에 말 그대로 그냥 데이터를 달라고 하는 것인데 이게 아웃풋 밸류가 지금 뭔가 그레디언트가 굉장히 많이 흐르고 있는 그런 정보들 있잖아요. 그런데 그쪽에서 그냥 데이터를 치시면 아웃풋 그레디언트 정보가 없는 텐서가 리턴이 됩니다. 그레디언트가 흐르지 않는 그런 텐서가 리턴이 됩니다. 그리고 모델 이밸류에이션과 토치 노그레드의 차이점. 사실 이거 두 개가 완전 다른 것인데요. 모델 이밸류에이션이란 거 하는 건 뭐냐면 이제 나중에 배치 노멀라이제이션이나 드랍아웃 같은 걸 굉장히 많이 사용하게 되실 거예요. 그렇게 됐을 때 이제 이거는 트레이닝 때와 테스트 때 좀 다른 행동을 가져야 하거든요. 그렇게 했을 때 모델 이벨을 사용하면 배치 노멀라이제이션이나 드랍아웃 같은 게 이밸류에이션 타임 모드로 바뀐다 정도입니다. 이제 토치 노그레드는 이제 이밸류에이션 타임 때 우리가 그레디언트를 하지 않겠다라는 거고요. 그래서 그 두 가지는 완전 다른 거라고 생각을 하시면 됩니다. 라벨이 없는데 W를 어떻게 알아내는지. 이제 이 경우 같은 경우에는 뭐 예를 들면 다이멘션이 1이잖아요. 그러면 결국에 다이멘션 1짜리 무언가를 하겠다는 건데, 그러면 뭐 대표적인 게 로지스틱 리그레션 같은 게 있겠죠. 뭐 0 혹은 1 구분하는 것이다. 혹은 그냥 리니어 리그레션. 뭐 예를 들면 뭐 집 가격이 얼마인지 맞추는 그런 케이스라고 한다면 이제 아웃풋이 1로 나와야 되는 거잖아요. 이제 100만 원 이런 식으로 딱 다이멘션 1짜리가 나와야 되는 거기 때문에 그런 경우에는 크로스 엔트로피 로스가 아니라 다른 로스를 사용을 합니다. Yes, thank you, William. So I think this is the really good answer. So does anyone have other questions?
저기 혹시 괜찮으시면 말로 한번 여쭤봐도 되나요?
네네.
여기 방금 전에 리니어 펑션 설명해 주셨을 때요. 그러니까 제일 그 강의
네네.
첫 부분이었는데 저희가 토치로 x만 만들어서 x에 해당하는 y 값이 없어 보였는데 어떻게 그러니까 지난 수업에서는 라벨 y를 줘가지고 이렇게 그 SL 하는 걸 봤었는데 여기서는 y가 안 보이는 것 같아서요.
네네. 지금은 그냥 말 그대로 예시를 보여드린 거고요.
근데
이제
네. y가 없는데 얘가 어떻게 y를 출력할 수 있는지도 잘 모르겠어서. 예, 그 부분이
여기
맞습니다.
말씀이신가요?
네, 네, 맞습니다.
네. 지금 저희가 리니어, 혹시 다른 분들 이제 질문 없으신 분들은 나가셔도 될 것 같습니다. 일단 리니어 NN을 했다는 것은 이제 WX 플러스 B를 했을 때 아웃풋이 1짜리를 만들고 싶다는 건데요. 그럼
네.
저희가 이제 리니어 펑션을 만들었잖아요.
네.
그럼 이 리니어 펑션에 이 X를 포워드를 하면 이제 Y가 다음과 같은 쉐입의 Y가 나오게 됩니다.
예, 질문은 이제 그
네.
지난 시간에 배웠던 거는 실제 트레이닝 하기 위해서 이런 X에는 이런 Y가 해당한다고 이제
네네.
트레이닝 시켜가지고 W나 B를 구해서 그 다음에
네네.
그러면 테스트하기 위한 X를 집어넣었을 때 Y는 어떤 값이라 예측하는 걸 배웠었는데요. 물론 그때는 딥러닝은 아니었는데 근데 궁금한 것은 지금은 만들어 놓은 X 텐서가 그냥 X 값만 있고 거기에 해당하는 Y 값이 없는데 어떻게 얘가 W랑 B를 계산할 수 있다는 건지.
이거는 말 그대로 함수
예.
정의를 말씀드린 거고요. 어떻게 함수를 정의하느냐? 근데 말씀하신 대로 학습을 해야 되는 거잖아요.
네네네.
네네. 그런데 지금 여기는 정의에 대한 것만 설명한 파트고 학습에 대한 건 설명이 없습니다. 말씀대로 학습을 하고 싶다면 뭐 예를 들면 저희가 데이터셋이 있으면 되겠죠? 그래서
네.
뭐
네.
y 마이너스 뭐 그거에 해당하는 레이블이 있을 거예요. 뭐 그렇게
네네.
된다면 뭐 이런 것들을 미니마이즈 하고 나서 다시 출력하게 되면 될 것 같습니다.
네. 그러면 지금 49번 행이라고 써 있는 거기에 리니어 펑션에서는 W랑
네네.
B는 그냥 랜덤한 아무 값이나 여기서
네네.
PC에서 알아서 만들어서 그냥 곱해줬다는.
네네.
WX.
맞습니다.
네. 감사합니다.
네, 감사합니다. 함수가 리니어하지 않은 경우에는 어떻게 적용할 수 있나요? 지금 말씀대로 먼저 성준님 먼저 말씀드리면 될 것 같은데 학습된 결과가 아니고 유미에게. 네, 이거는 지금 완전 랜덤한 값이고요. WB는 이제 초반에 그냥 랜덤한 값을 파이토치에서 알아서 설정을 해줍니다. 이제 리니어하지 않은 경우에는 저희가 커스터마이즈를 다음과 같이 하면 됩니다. 예를 들면 지금 이 모델 같은 경우는 리니어하지가 않잖아요. 이제 중간에 런 리니어 펑션이 없기 때문에 리니어하지 않은 건데 그런 경우에는 다음과 같이 커스터마이즈해서 넌리니어하게 만들어 주시면 됩니다.
제가 잠깐 설명할게요.
네네.
So someone asked the roles of the backward and Autograd and step and all that. I think let me see. 누군가가 지금 그러고는 backward optimizer step. So what's the relationship between lost backward and optimizer step? And I think TH even briefly explained that, but okay, I'm gonna answer that question first, and then gonna address other questions. So if you look here, there's lost backward and there's optimizer step. And lost backward is the you are calling the chain of derivatives starting from the top to the bottom. So let me draw a simple picture here. If you remember the z and x and y's from the previous class, this is your z, this is your x. And if you call z backward, what you're getting at is calling this will give you dz dx. And of course, that's when x requires grad initialized or declared. So if there's no node that requires grad, then calling this doesn't really work. But when you call this z backward or loss backward, then you are doing chain of derivatives. And along the way, I've said in class that along the way, you are basically what you're doing is you're calculating your deltas, which is the error that is caused by the input to the current node. And using the delta, you can calculate the gradients of the loss with respect to the weights if necessary. If there's weight involved, if there's some learnable weights in this node, if there's another learnable weight in this node, like I'm going to use W2, W1, then along the way, using the delta, you could multiply delta with the pre-activated value or the input from that would be here. You can multiply delta with this value to calculate dz or d loss divided by dW2. Right? I hope everybody remembers this. That's the reason that we're calculating deltas all the way from when we're doing back propagation. So this happens when you call the backward command. When you execute this, this will happen here and another. So this will be delta 2 actually. So delta 1 times a. So this is a1. This is a0, and dz dw1, like this. So along the way, so these values will be saved in the context or the container that I talked about. So you could save you can save a lot of stuff. Like you can save your input, you can save your miscellaneous. These are saved in your container when you're doing backward. And then once you've done this, you want to update this to the next step. So this should be your W2. New is W2 old minus step size, which is 0.05 in this case, because you're using gradient descent, by dz dw2. So this is why why we call this function. So when you call step function, this happens to W2 and also W1, or all the parameters in your entire network. W old, like minus step size, DZ, and DW1. Right? Because this value comes from here. This value comes from here. So backward is when you calculate the gradients of your loss with respect to all the learnable parameters in your network. And step is when you update your parameters, all the parameters in your network, with using the gradients that you've calculated in the backward step. So that is why you alternate this step. You do backward and then you do step, and then you go back again, load your mini batch of images, transfer that into your video memory in GPU, and then you do forward propagation to get the y value, the y hats, your prediction. Calculate the loss. Do a loss. You do a gradient. Do a back propagation, which is essentially doing a derivative of your loss with respect to all the parameters. Getting that, you update it with the step, and then from time to time, you calculate the performance of your model. That is the entire loop that you want to do until your models are finally optimized. All right, I hope everybody is making the connection between the theory that we talked about in the previous class and what you're doing in the PyTorch code here. W1, W2 연결되어 있고 W2 업데이트. 네. 모든 건 다 독립적으로 업데이트됩니다. 사실은 W2가 먼저 업데이트되고 W1이 나중에 업데이트돼요. 왜냐하면은 이 델타를 이용하는데 델타2, 델타1 이용하잖아요. 델타2는 W1의 에러를 이미 갖고 있고 델타1은 이미 그 아래의 에러를 이미 갖고 있기 때문에 어떻게 보면은 사실 순차적으로 백워드로 하면은 제일 먼저 위에 게 업데이트되고 그 다음 게 W1이 업데이트되고 그 다음에 그 밑에 게 업데이트되고 그런 식으로 됩니다. 네, 맞습니다. 트레인 로더가 사이즈를 넣을 때 만약 GPU를 여러 개 사용하게 되면 트레인 로더에 넣는 트레인 로더에
이거에 대한 답변 드리자면 그게 GPU를 여러 개 사용하기 위한 툴에 따라서 다른데요. 데이터 파랄렐이라는 툴을 사용하신다면 아마 토탈 배치 사이즈랑 동일하게 될 거고요. 이제 디스트리뷰티드 파랄렐이라는 걸 사용한다면 이제 배치 사이즈 곱하기 GPU 개수가 토탈 배치 사이즈가 될 것으로 알고 있습니다. 이건 아마 직접 찾아보시는 게 빠르실 것 같습니다.
잠시만요. 그 백유미님 질문 답변 드리기 전에 또 있네. 커스터마이즈 액티베이션 함수를 적용하는 건가요? 커스터마이즈 하라는 얘기인 건가요?
네네. 이거 맨 마지막 이제 자유롭게 커스터마이즈 할 수 있다를 말씀드리고.
그거는 뭐 레이어를 더 추가하셔도 되고 아니면 시그모이드 when the TA asks you to customize your models to get a better performance, that means you can add more layers. You can change your activation functions from sigmoid to 10H or ReLU, or you can use dropout. You can do whatever you want. 숫자 맞추기 예제에서 영구 학습별 학습으로 W 벡터를 구하는 것이 즉 W가 숫자별 학습으로 W 를 구하는 것이 무슨 뜻인지 잘 모르겠네요. 네, 그냥 어쨌든 W가 128과 10이 아닙니다. W는 28 곱하기 28이니까 780 몇인가 그러는데 하여튼 28 제곱 곱하기 10이에요. 그래야지 28과 28 이미지를 10개의 클래스로 보내버릴 수 있기 때문에 그래서 W는 28 제곱 by 10, 20 square by 10입니다. W는 그거를 학습을 하는 거예요. 실제 그 true 이제 그 예측된 y와 true y가 있으니까 그거에 이제 크로스 엔트로피 로스를 이용해서 W 학습하게 됩니다. 그다음에 zero grad는 어디예요? zero grad는 Okay, I'm going to erase the figures here. The zero grad. So the reason that we call zero grad is that whenever you call backward, each node in your computational graph, I said that neural networks are just a directed acyclic graph. Everything is represented as graph. So in your computational graph, each node has a member variable named grad, which we already saw in the. Where did we see that? Yeah. Here. Was it here? Yeah, here. Yeah. So each node has some member variable called grad. So this is where the gradient values are stored when you call backward. So when you call backward, you do back propagation and do a chain of derivatives. And whenever you calculate the gradient, you store that gradient value into the grad member variable. And when you call that backward twice, then another gradient value is added to the previous gradient value. So you want to flush that out. Each time you do a mini bench update, you want to flush out the previously calculated gradient values so that the new gradient values, you can calculate that, store that, and then use it in your gradient, in your parameter update. That is why zero grad is called each time in your mini bench update here. 혹시 이해되셨나요? 그러니까 그래드라는 한 멤버 변수에다가 계속 이걸 축적을 하기 때문에 이 제로 그라드를 부르지 않고 백워드를 계속 부르면은 계속 축적돼요. 그레디언트 밸류가 계속 더해집니다. 그래서 제대로 업데이트가 안 되기 때문에 미니 배치 업데이트 한번 할 때마다 계속해서 이 리셋을 시켜줘야 되는 거예요. 네, 혹시 또 질문 있으신가요? Any more questions? 맨 아래 말씀하시는 건가요? 커스터마이제이션? 여기요? 여기 말씀하시는 건가요? 여기요? 혹시 그냥 음성으로 물어봐 주실래요? 이거 치려면 시간이 오래 걸리니까. 백유민님.
네. 그 아까 논리니어한 경우에는
네.
그 커스터마이제이션을 통해서 해결할 수 있다고 했는데 그게 어떻게 되는지 잘 이해가 안 돼요.
아까 저 기훈님이 정확히 뭐라고 하셨었죠?
그러니까 함수가 리니어한 경우는 그냥 리니어 함수를 사용하는데 만약에 논리니어한 경우를 적용할 경우는 어떻게 해야 되나 했을 때 이제 커스터마이징 하면 된다고 했는데 제가 그 개념을 잘 모르겠어요.
그러니까 여기서 아마 그거 말씀하시는 것 같은데 요게 만약에 없고 얘도 없고 이렇게 하면은 지금 그냥 리니어한 거 FC1, FC2, FC3 계속 그냥 통과시키는 거잖아요. X를 넣어서 뽑고 그 아웃을 다시 FC2에 넣어서 뽑고 다시 FC3에 넣어서 뽑고 해서 결국 아웃이 나오게 되잖아요. 이러면은
네.
사실 그냥 매트릭스를 계속 곱한 거랑 똑같아요. 저번에 누가 말씀하셨지만 W2, W3, W4, W4, W5 하는 거는 W 하나 이용하는 거랑 똑같다고 그랬죠, 파워가.
네.
네, 그거 하고 있는 거예요, 지금. 만약에 여기서 시그모이드가 없었으면은 그냥 이렇게 계속 FC만 이렇게 가지고 태우면은 그럼 전혀 FC 하나 쓰는 거랑 다를 바가 하나도 없습니다. 그래서 이제 그 사이에다가 넌리니어한 액티베이션 펑션, 시그모이드나 아니면 타네이치나 아니면은 뭐 렐류나 이런 다른 하여튼 리니어하지 않게 이걸 약간 이렇게 구부려주는 쉐입을 구부려준다고 그러죠. 공간을 구부려주는 그런 넌리니어한 걸 써줘야지 얘가 제대로 여러 레이어를 쓰는 게 의미가 있어져요. 그러니까 이제 FC 리니어 레이어 통과시키고 시그모이드 쓰면은 이미 넌리니어해지고 다시 그걸 한 번 더 이제 선형 변환한 다음 또 넌리니어하게 만들고 또 선형 변환한 다음 또 넌리니어하게 만들고 이런 식으로 이제 그걸 번갈아 해주셔야지 레이어를 여러 개 쌓는 게 의미가 있는 겁니다. 그렇지 않고 그냥 리니어 레이어만 계속 쌓으면은 리니어 레이어 하나 있는 거랑 다를 게 하나도 없어요. 그거 말씀하신 걸 거예요.
그러면은 이제 어떤 함수에 적용하는지는 이제 데이터에 따라서 저희가 합리적으로 선택하는 건가요?
그렇죠. 네. 그냥 웬만하면 넌리니어 레이어를 안 쓰면은 작동이 안 됩니다. 세상에 있는 데이터는 다 넌리니어하게 세팅이 되겠죠. 그러니까 리니어한 거 함수 하나 가지고 파악하거나 표현할 수 있는 데이터셋이 되게 드물어요. 그러니까 지금 보시면 여기도 위에서 이제 로지스틱 리그레션에서 여기서 그때 성능 92%가 나왔잖아요, 지금.
네네.
그게 100%가 안 되는 거는 그러니까 이제 리니어한 걸로 해결할 수 없는 숫자들이 있다는 거예요. 어떤 샘플이 있고. 그러니까 이게
네.
미묘한 함수로 100% 표현이 되는 샘플이었으면 MNIST가 그러면 이게 100%가 나와야겠죠, 성능이. 100%가 안 나온다는 거는 MNIST 그 디짓 이미지라는 게 리니어한 것만으로는 완벽하게 표현이 안 된다는 얘기고, 그래서 여기다가 이제 이런 넌리니어한 걸 넣어주면 성능이 더 올라가게 되는 겁니다.
아,
혹시 이해가 되셨나요?
네네네, 알겠습니다.
네, 알겠습니다.
감사합니다.
네. 또 질문 있으신가요?
예, 교수님, 방금 전에 설명해 주셨을 때요, 로지스틱만으로 92%였기 때문에 더 이제 좋게 하려고 이렇게 한 번 더 구부러졌다고 설명해 주셨는데요. 근데 그 로지스틱 안에도 이미 그 시그모이드 펑션 비슷한 그게 들어가 있는 거잖아요.
로지스틱 안에 시그모이드가 없고 로지스틱 안에서 리니어한 건데 그거를 0, 1 사이에 probability value로 만들려고 시그모이드가 들어가 있는 거예요.
아, 네네. 그러면 그렇게 나온 결과를 다시 한번 구부려 준다는 말씀이신 건가요?
아니, 그거는 그러니까 로지스틱 리그레션에서 시그모이드를 쓰는 거는 0, 1로 맞춰주려고 하는 거니까 데이터를 표현하는 거랑 상관이 없고 그냥 단지 이게 몇 클래스냐. 그래서 지금 이제 멀티노미얼 로지스틱에서는 28 by 28이라는 이미지를 10 클래스로 지금 줄여야 되잖아요.
네.
0, 1, 2, 3, 4, 5, 6, 7, 8, 9니까.
네.
그거 한 다음에 그 다음에 이제 함수 값을 이제 그 값을 10, 10차원의 값을 그 확률 값을 만들어 주려고 시그모이드를 쓰거나 소프트맥스를 쓰는 거니까 그 전 단계에서 뭔가 일어나야지 그 마지막 단계에서 딱 한 번 그때 probability 밸류 맞추려고 쓰는 거는 별로 그 넌리니어 레이어랑 상관이 없는 얘기예요. 왜냐면 그 10차원을 줄이기 이전에 이미 마사지를 해주고 있어야 돼요. 그 넌리니어 레이어를 쓴다는 개념은. 그러니까 이제 28 by 28 이미지가 들어왔으면 그거를 뭐 200차원을 한번 줄이고 100차원을 한번 줄이고 그럴 때마다 이제 넌리니어한 걸 쓴 다음에 마지막에 10차원을 줄여가지고 확률 값을 구하는 것이 이제 목표지. 그 전까지 계속 리니어하게 하다가 마지막에 딱 10차원을 줄인다면 그때 이제 시그모이드 써가지고 확률 값을 바꿔줬다고 하는 거는 넌리니어 레이어 썼다고 말할 수가 없어요.
예, 근데 그 지난 화요일 수업 시간에 이렇게 중간 레이어, 히든 레이어 줬을 때 히든 레이어마다 이렇게 액티베이션 한다고 알려주셨던 것 같은데
네,
그러면 거기에 대응하는 게 지금 이렇게 주석 처리한 아웃 셀프 점 시그모이드 하는 게 거기 대응되는 거인 거죠?
네 맞습니다.
아, 네. 감사합니다.
러닝을 돌리면 실행할 때마다 확률 값이 다른데 몇 번이나 반복해서 평균해야 하죠. 학습할 때는 확률 값이 계속 달라져요, 당연히. 왜냐면 계속 파라미터 업데이트 하니까. W랑 B를 계속 업데이트 하잖아요. 그레디언트 그 디센트를 이용해서. 그러니까 그때마다 당연히 확률이 달라지겠죠. 근데 이제 학습 끝내고 나서 이제 W랑 B를 고정시키면 그때부터는 똑같은 인풋을 나오면 항상 똑같은 아웃풋이 나옵니다. 그러니까 더 이상 변동성이 없어요. 우리가 뭐 베이지안을 쓰지 않는 이상. 그래서 그 소정님의 질문은 약간 핀트가 어긋나 있다고 볼 수 있습니다. 모델 리뷰랑 대치 노멀라이제이션 할 때 사용한다는 테스트 시도 모델에서 테스트 시에는 모델 리뷰를 사용해야 됩니다. 그러니까 이제 지금 트레이닝 할 때랑 그러니까 학습할 때랑 테스트 할 때랑 다르게 동작해야 되는 컴포넌트가 들어갔을 경우에 대치 노멀라이제이션 드랍아웃처럼 그때 이제 모델을 이벨 모드로 할 건지 트레인 모드로 할 건지 설정을 해줘야 되는데 당연히 학습할 때 트레인 모드를 쓰고 테스트할 때 이벨 모드를 쓰셔야겠죠. 사용한 문제가 있을까요? 아니면 테스트 시에는 모델 이벨을 사용해야 됩니다.
네, 교수님, 제가 이 파트를 조금 대충 설명드린 것 같은데 지금 이재원님께 설명을 드리자면 배치놈이나 뭐 드랍아웃 같은 게 트레이닝 샘플 뭐 드랍아웃이라고 가정을 하면 이제 트레인 모드일 때는 매번 좀 랜덤한 값이 나옵니다. 하지만 테스트 할 때는 저희가 이제 고정된 값을 원하잖아요. 그래서 모델 리벨을 해주면 이제 고정된 값을 계속 꾸준히 얻을 수 있습니다.
네, 뭐 더 이상 질문 없으시면 오늘은 이 정도로 마치도록 하겠습니다. 혹시 더 질문 있으시면 클래스 한번 올려주세요. 네, 그 지훈님 수고하셨고요. TA 하시느라.
네, 감사합니다.
네, 모두 다음 주 화요일에 뵙겠습니다. 감사합니다.